Welcome to Unit 4, Equilibrium. Now, here, oh, I look weird. I don't know if that fixed it. Um, Here's the thing about Unit 4. The equilibrium stuff that I'm about to introduce you to is highly ingrained in Units 5 and 6, which is November and December. What that means is if you don't get this, if I lose you in Unit 4 and you do really bad on this test, it's going to echo for the rest of the semester. And you don't want that to happen to you. Like in kinetics, if you were bad at kinetics, I mean, that sucks, but you're going to do fine in equilibrium for the most part. But if you're bad at equilibrium, units 5 and 6, they use all of this stuff a lot. So you've got to be good. So let's be good at understanding the stuff I'm about to start covering. Dun, dun. Okay. So what is equilibrium? Look here. I want you to understand what we're doing. I kind of mentioned it when I showed you your roadmap yesterday. In a nutshell, equilibrium is when a reaction stops. If you want to go a little bit deeper on a way to say that, you could say it's when the forward rate and the backwards rate are the same, because that would mean that it's stopping. It's moving forward at the same rate it's moving backwards. Here's what it's not. Equilibrium is not the amount of reactants equals the amount of products. There is that misconception that exists, and College Board knows that you have that misconception. Make sure you have your slides up. So let me say it one more time. If you're asked to define equilibrium, it's where a given reaction's not doing anything because the rate forward equals the rate backwards. Moving towards the products as quickly as it's moving towards the reactants. Nothing's happening. Equilibrium does not mean you have the same amount of reactants as you do products. Some of you really want it to mean that, and it doesn't mean that at all. So don't let the College Board MCQs mess you up because you want to have this misperception. Anyway, so you can see that summarized up there on our first slide. Let's start getting into the way that we can study a reaction that's not moving. Well, really, what we want to know and use for a reaction at equilibrium is the big question is when it stopped, when the reaction was no longer doing anything, were there more reactants or products? And we have a weapon to figure out the answer to that question. We call it K. Now, this is a different K than your rate law K. I don't know why they chose K for variables so often in chemistry. They didn't ask me 100 years ago for my opinion, but it is kind of annoying. So the K that we've been studying in kinetics is totally different than the K that we're going to be studying in equilibrium. But what we do is we do a little bit of math that I'll show you soon, and we get a value for K, and we can use that number to figure out whether there's more reactants or products. I'll show you how we draw that conclusion in a moment, but first, here's some stuff about this new equation, because this right here, y'all, this is your new best friend. This is our application of figuring out which direction an equilibrium reaction is favored. By the way, of course, that's the wrong arrow. Do you remember the equilibrium arrow from 2 units ago? Right? It was called the equilibrium arrow. It was the double-sided arrow. We used it for weak samples that weren't completely dissociating. Anyway, that's the only arrow we'll be using here. I have the wrong arrow up there. But it'll always be a double-sided arrow showing that the reaction is reversible, ultimately. But here's the way our new equation works. See this reaction up here? The substances are capital letters. The lowercase letters is the mole ratio, the coefficients. What we will do mathematically to find this K value that will tell us whether there's more reactants or products when the reaction stopped is we will put the products as a numerator raised to the power of their coefficients over the reactants as a denominator raised to the power of their coefficients. And that's how we'll be running equilibrium for several units. So this is the equation. What do the brackets mean in that equation? Molarity. Brackets always mean molarity. So, a couple things. K and Kc are synonymous. The C stands for concentration, which we know means molarity. In other words, if you're using brackets, you're finding K or Kc. They're the same. To have a concentration, though, you have to have dissolved particles. The only states of matter that have dissolved particles are aqueous and gaseous, meaning that if you're given a reaction, only substances that are aqueous and gaseous can go into this equation. You'll see it soon. Kp is pressures. It's if you're going to do this, but with pressures instead of concentrations. We don't use brackets for pressures. We use parentheses, which was a little tidbit from last unit. Anyway, but only gases have pressures. Now, I'm kind of over foundationing you right now because this makes a lot more sense when you see it in action. But I want you to know that these initial slides are really good to go back on if you get confused on why things are happening. But if there was a most important thing that you're going to read today, it would be these bottom statements down here, because what you'll ultimately do is throw some numbers into this equation, and it's going to spit out a K. Now, that K doesn't have units. That's why it's really different than the rate laws, right? Because the rate law K had a bunch of different units depending on the order. Equilibrium K is all about magnitude. We just want to know, is it a big number or a small number? If you put all the numbers in there from the reaction and it spits out a number greater than 1, that means that when the reaction hit equilibrium, there was more products. If you put in all the numbers and K ends up being less than 1, not negative, less than 1, then there's more reactants. It's favored backwards, we would say. And that's the big conclusion to come to. Random reaction, random concentrations. But without doing it, I can know whether there'll be more product or reactant when it stops. We'll apply this idea soon, but first we're going to be a little abstract. College Board loves their graphs, so I want to show you how an equilibrium graph can lead you to a balanced equation. Now, my x-axis isn't labeled. It's going to be time. So please label your x-axis time. That's my bad. Using the kinetic data here, because look what's being put against each other, right? It's molarities changing over time. And you can see that these 3 different substances are being altered. From them, I can identify reactants, I can identify products, I can identify mole ratio. And it starts with this idea. Look here. In a reaction, do you expect reactants to increase or decrease during a normal progression? Decrease, right? It's the whole point of the reaction. The reactants are used up while the products are formed. If you understand that idea, then you can pick the reactants and products right away. Look at the lines and whether they're going up or down. What is the only line that's decreasing? A, which means in this graph, I know that A is the only reactant. Hey, look at my arrow. This is the only arrow you're allowed to use the next couple weeks. All right? Which means the graph clearly has B and C increasing. Does everybody see it? All right. So there's the skeleton equation. Another thing I can figure out from my graph is at what point did equilibrium happen? How long did it take for the reaction to stop? Well, if you look back, what you're looking for in order to figure that out is you're looking for plateaued lines. You're looking for the moment that all three, in this case, of the substances plateaued, which means they no longer were changing anything. Now, I want to warn you, this can be a bit subjective. There's a chance that we're about to disagree on what time all three of those lines went flat. The good news is that on Canvas and when College Board gives you an exam eventually, there won't be any. It'll be very clear whether or not you understand what I'm teaching and what you're supposed to understand. But take a stab. What do y'all think? Let's disagree. At what point in time do all three lines go flat? Did you say 500? I heard a 500. Let's look at why. I'm glad that you said that. Let's look at why 500 is definitely not a good answer. I know, right? Because look here, see at 500 how right after that mark the green line is clearly still going up, the red line is clearly still going down. There is still changes, so that would be an answer that would not give you credit. I would say 900 is probably pretty safe. 900 seconds is probably a pretty safe time to say that these lines have flattened out, maybe a little bit before, who knows, but that's what you're looking for. Finally, you can find the mole ratio. You know kinetically that the coefficients of a reaction talk to each other in regards to time, right? You just got tested over that. The best way to find that mole ratio is to take a block of time and look at how the three, in this case, substances changed over that time. The best block of time to pick is the earliest block, because that's when stuff's changing the most dramatically. So let's take this first block of time, 0 to 250 seconds. About how many squares does A move through? 2. Just under 2. About how many squares does B move through? Just under 1. About how many squares does C move through? Just under 1 during that first block of time. So, comparatively to each other then, it is a 2 to 1 to 1 mole ratio. Let's see if any of that stuck. I'm going to give you 60 seconds to see if you can answer these 4 questions. It's the exact same thing. I think these lines are actually clearer. And then we're going to draw cards. Yeah, E cubed is good. Let's take a look at how we're doing. Some of y'all still counting squares. Let's just get reactant or reactants from someone. Let's head over to cluster 1, seat 6, and pick you twice in a row. Hey, 1-6. What are the reactants? I agree. It is B and A. Equilibrium arrow. Any questions on that? They're both decreasing. Which means it must be C that is the product because it's increasing. The lines are going up. Now, I know you're sitting there wondering, but I put A plus B. It's the same thing. No one cares. All right. Equilibrium time. All right, let's draw a card. Let's see if we can get some equilibrium time. Let's go to cluster 1. There's no way, right? Cluster 1, seat 6. Look at this. Look at this. No, not products. No, the product C. I want to know the equilibrium time. Take a guess at how long did it take equilibrium to be reached? Yeah, I think 9 seconds is good. I'm a little weird. I said 9.5 seconds because I think it's a little bit past that point. But the only reason I said that, if you look here, it looks like it hiccups one more time after the 9-second mark, and then they all have to be flat. But all the lines need to be flat, so probably right past 9 seconds. All right, and then does anybody want to yell out their mole ratio? You can just do it. 2 to 3 to 4. Yeah, if you take that first block of time, B goes through 2 squares, A goes through 3, and C goes through 4. Who's got questions on how to do this? No, when you're counting when you're doing the mole ratio. Yeah, when you're doing the mole ratio, you pick one block of time and you compare all 3. Usually the first block of time is the best. All right. Well, kudos. You're a little bit into equilibrium. That's a bit more abstract. This next thing is where the highest repetition exists. So, I just want to remind you of a few things before we start. Remember, we have a general equation we use. It's reactants over products, both raised to the power of their coefficients to get K. Once we have K, we care about whether it's bigger than 1 or littler than 1, and that tells us whether there's more products or more reactants. K has no units. It's all about magnitude. I just need to know, is it big or little? And you see the phrase unsubstituted there? That's important, and let me model it for you. Okay, so here is a standard question. It gives you some stuff here. We've got a balanced equation. Hey, remember, only for Kc, for concentration K, only aqueous and gaseous can go in. That's important because if any of these were solid or liquid, we would just ignore their existence for calculating K. But do you see how they're all gaseous? So we're not going to ignore any of them. It gives me concentrations at equilibrium of each of them. That's important because the input that we're about to do to our equation, those numbers have to be at equilibrium. They can't be like at the beginning. They have to be the numbers at the end. And then we'll plug them in as I'm about to show you. And it gives me those values and it wants Kc. So, with that said, just killed you with the ruler. Let's start with what's called an unsubstituted equation. Here's what I mean. We want to find Kc, but instead of putting in the numbers, I'm going to show what the substances are. So up top goes the product raised to the power of his coefficient. And then on the bottom goes the reactants, hydrogen and iodine, raised to the power of their coefficients, which of course is 1. This is called the unsubstituted equation. Some of you are going to try to save time by skipping it because you're going to see that you don't really have to do it. You could just plug the numbers in and go about your life. But I want to warn you, 1 or 2 times in May on the FRQ, you can get a point for showing an unsubstituted, and they don't always tell you where it is. This is a great habit to be in. They've told me to tell you this. To even if you're not asked to show this, to show it. And then substitute. And there's the numbers. Remember, the numbers are already at equilibrium, so it makes this next part really easy. We'll just plug them straight in, which is 0.3 for the product. And then the reactant values are 0.012. And iodine is 0.15. I want you to beat me to an answer, but don't let order of operations beat you. Look. If you divide that number by that number and then multiply by that number, you're going to get a wrong answer. You need the bottom product first. So the safe way to do it is to protect this in parentheses in your calculator. Don't write it like I just did. All right, you don't want to mess up your pretty work. But in the calculator, I would protect the groupings of numbers for order of operations. There's a square on my screen. How many sig figs should your answer have? 2 sig figs count here. Be careful. Nothing is sadder in May than losing a point for sig figs. I get 50 with a decimal. If you did not get 50 with the decimal, run it again. You just did. It's probably this. These parentheses right here that aren't really a part of the problem is part of your problem. Verify that you can get 50. But what's the big conclusion that we're supposed to draw? That work is fine. That's the answer. But remember, I want to know at equilibrium, is it favored forward or reverse? Which direction? Forward. Go back a couple slides. If the number's bigger than 1, then there's more products. And of course, the products are on the forward side. That's the big conclusion. There will be more of the more of the hydrogen iodide than of the hydrogen and the iodine. Right? So different amounts, because equilibrium doesn't mean they're the same amount. Just means they're the same rates. I believe in your ability to do this, and a lot of this unit is just plugging and chugging into this, or a lot of this assignment on Canvas. And we'll practice another one, but I want to show you something harder right now before you get all numbed over. But this is it, y'all. This is equilibrium's most foundational skill, is to input these values to then draw a conclusion based off this K. But here's a couple weird things that you might be asked to do. One of them is converting between KC and KP. Remember what that means. KC is exactly what you just did, but you use concentrations. KP is where they're using pressure values instead. But we have this dumb equation where you can actually make those two ideas talk to each other. So here it is. The best way to show you how to use this is to just do a problem with you. But I want to point out that R is a gas constant, right? It talks to pressure nicely. And when you did PivNert last year, you actually used this number, all right? That's a constant that you've seen before. The good news for you is that this number is on your formula chart. This is on your formula chart. So there's no memorizing here or anything. You've actually, the N was moles in PivNert, and it's going to mean moles here also. So with all that in mind, let me show you how we do this conversion. It's pretty much just a plug and chug. All right, so we've got our friend right here. So let's check it out. Let's see what we have here. They did give us a KP of 0.25. They did not give us a KC because they want us to find that. I'm going to sub in an X for a variable. We know that R is constant at 0.08206. The T is temperature in Kelvin, which is given at 1100. And delta N is where you might mess up. It's raised to the power of delta N. Look here. Delta is change, N is moles. Here's what you need. You need the gaseous product moles minus, because it's change, right? Finish minus initial. You need the gaseous product moles minus the gaseous reactant moles. Keep in mind that the mole ratio gives you those values, which is the coefficient. So listen to me say it again. All of the gaseous product moles, you get a number, minus all of the reactant gaseous moles, another number. It's the subtraction there, the difference. So if you look here at the problem, all right, the SO3 right here is gaseous, all right? It says so right there. So it's going to be those 2 moles of gas minus how many reactant moles of gas are there total? There's 3, because there's 2 there and 1 there. And what is 2 minus 3? Sorry? -1. 2 minus 3 is -1. You should be able to beat me to an answer. I'm just going to show the algebra but make sure that you are working as well. I get 23. I need you to look at my algebra and tell me if you don't understand something. No silent suffering. Yeah. We all right? All right, let's do another one. We'll draw some cards this time. Make sure we are on our game. It's another very similar question. Remember, this is for converting between the two different measurements of K, concentration versus pressure. All right, so let's take a look. Here we go. Do we have a KP? Again, it does. 1.04 is given. Do we have a KC? No. Wants us to find the equilibrium constant based on concentration. We know that R is a constant value of 0.08206. Temperature must be Kelvin. And it's 852 given. And here's where I want to draw a card. I want everyone to look at the reaction and privately come up with a delta N. Remember, delta N, product gaseous moles minus reactant gaseous moles. Let's head on over to cluster 4. We finally went somewhere different. Seat 1. 4-1. What do you think? The guess is 4. Do you agree or disagree? 4 is correct. Because look, gaseous 1, gaseous 3, that's a grand total of 4. Minus, there are no reactant gases. So it's 4 minus 0. Everybody cool with that? Beat me to an answer, please. You should be at 3 sig figs on this question. I get 4.35 E negative 8. No units, because K has no units when it's the equilibrium constant. But I would like to ask somebody whether it's favored in forward or reverse, so let's call on someone. Let's go over to cluster 5 and go to seat 4 at Aspen. Pretty much just you and me today. Do you think it's favored in forward or reverse? The guess is forward. Agree or disagree? Well, I heard both agree and disagree. What do you think at home? That'd have been weird. I disagree. It is not favored forward because this number, you see the E negative 8? This number is less than 1. If K is less than 1, it's favored in reverse. So we are favored towards the reactants, yeah? Now, as promised, we're going to do one more of the more standard products on top of reactants raised to the power of their coefficients to end class. But one more little idea. They can ask you to find K of the opposite direction, of the reverse reaction. It would be a different K value. Here's what the trick is. It's really simple. If you know what the K value is for the way it's written forward, the K value for the way it's written backwards is just the reciprocal. Do you know what that word means? All right, where you flip the equation? It's the number 1 divided by the answer. So we'll do it on the next question. But if I wanted to know the K for whatever this problem was, it's not posted anymore. What I would do is I would take that K value, that orange number, and I would go 1 divided by it, because that's what a reciprocal is. I'll show you on this last problem. Let's take a look at our final problem. And I want you to see how this is kind of a mean problem, because they want you to do a bunch of AP stuff. Look here. Remember, our equation for equilibrium, products over reactants raised to the power blah, 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 lives in brackets for Kc. This wants us to find K, which is the same as Kc. However, brackets mean molarity, right? Look at the units they give us here. They give us moles. Moles is not molarity. Well, that's annoying. How do you find molarity? M equals moles over liters, right? Molarity is moles divided by liters. Look at what they do give us, though. They give us moles of each of the items, and look. They give you liters. So what you have to do is an annoying first step and convert all of them to molarity. Now, I only have 6 minutes, so I'm going to have to kind of push through and just show you this. So what this problem wants me to do is turn those mole counts into molarity counts, which is easy, just annoying, and then plug them into our equation. Keep looking. What's our equation? It's the equilibrium equation. Products over reactants. So you know what's going to go on top? Both of those. This one, though, will be raised to the power of 2, and he'll be raised to, well, nothing, power of 1. Over the reactants on bottom, him, raised to the power of 2. But look, it doesn't just want K, it wants K in reverse. We're having so much fun. So, take a look here. And you'll see that I've already begun the excitement. Now, I'm going to post this on Canvas. If you want to copy it down right now because you care and that's the way you operate, fine, whatever. If you don't want to copy it right now because you'd rather focus on my words, that's fine too. I'm going to post a picture of the whole board on Canvas. It's your call. But I want you to see that I've done exactly what I said we needed to do. Those are the 3 substances on the screen. The numerators here are the 3 mole counts that they gave me. The denominators is the liters that they gave me, because I know that moles over liters is molarity, and I know that my equation requires molarity. So here is my simple conversion to molarities, which is what was given in that earlier problem we did. They had already given us equilibrium molarities. So the black values are those, yeah? Here's the unsubstituted equation. All right? Those are the products. That's the reactant raised to the power of their coefficients. Yeah, yeah. So all I have to do is plug the black numbers into those spots, and it'll give me K. But remember, it doesn't want K. It does. But it wants K for the reverse reaction. So look. Here's my substitutes. All right, so I took the molarity values, put them into those spots, so it looks like that. I ran the math. The brown number is the answer in terms of K forward. But do you see how I get the K in reverse? I took that brown number and I did the reciprocal, which is 1 over that number for a final answer. Don't put your stuff away yet. I have one more point to make. Sorry. Now, if you're doing that thing where you're copying the board because that's how you are, stop for a second because this isn't written on the board and you want to hear it. You see this K value right there? Does that mean the reaction's favored in forward or reverse? Reverse. That number is less than 1. So get that. It's written out on the earlier slide. That number is less than 1 because of the E negative 4. It's going to move the decimal back. So it's favored in reverse. So you know what that means? That means that this dude is the favored substance. NOCl is favored. No matter what, it's favored. There's going to be more of that. So look what happens when we reverse it. If you reverse the reaction, the reactants become the products and the products become the reactants, right? That makes sense. And look what happens when the NOCl, that reactant that we said is favored, if he becomes the product because we reversed it, do you see what K does? Who does K favor now? Forward, the product, which is still the NOCl, because in reverse, that reactant became the product. So it all talks to itself very clearly, giving you the same result no matter the direction. And I love you.